Okay, thank you very much for the invitation. So everything I talk about will be joint work with Michael Stoll. So let me start with the theorem of faultings. Well, I guess this is not joint work with Michael Stoll. But okay, so I think you all know this. So if C is a curve of genus greater than 1 over Q or over a number field, well, I'll talk about Q for this talk. So then the set of rational points on the curve is finite. Okay, but I'm all right. So in this talk, I want to talk about what happens to this set as you vary C in a family. So, and the family I'm going to consider is the family of all hyperelliptic curves of odd degree. So C will be the smooth projective model of the curve y squared equals f of x, where this f of x is a polynomial. Well, I can assume it's monic, separable, so and of degree odd degree, so degree 2g plus 1. Okay, so all right, so then you can write down this smooth projective model explicitly by taking in a weighted projective space where you homogenize f, except you homogenize it to a degree 2g plus 2 polynomial, and that's so that you can make have y have weight g plus 1 and have an equation that makes sense. So you can check that this thing is a smooth proper curve, and it's the smooth projective model of this. And one advantage of doing this is you can see where the other rational, you can see the rational point infinity here. It's just the one where z is 0. I mean, because this thing is still divisible by z. So there's a rational point on this. That's in the homogeneous coordinates. It would be this. So okay. All right. So every curve in this family has one rational point, and we want to say what happens what happens in general for the are there other rational points on this curve. So let's see. So these both move, right? In principle, yes? Yes? Okay. All right. So all right, so here's the main theorem. So myself and Michael Stoll. So the first part is that for each g at least 3, the fraction of such curves satisfying, let's see, the fraction of such curves satisfying, well, having no extra rational points, such that the set of rational points is just this one point, is first of all, it's positive. Still don't know the answer for g equals 2. Anyway, so all right. So and then also this fraction, at least it tends to 1 as the genus goes to infinity. And finally, yeah. So in fact, you can make this quantitative. In fact, it is at least 1 minus 12g plus 22 to the minus g. And the third thing is that, well, there's a p-adic method called Chaboty's method, which you can do at any prime, but I'm going to apply it at the prime 2. And the claim is that this method effectively determines the set of rational points. So this is going to be the method by which we show that there are no other rational points. It determines the set of for such a positive fraction. So yeah, and I think this is the first time that you really had an effective method for a very large family of curves for determining the set of rational points. At least for in the case where the curve actually has a rational point. I mean, of course, you can also write down large families of curves that have no real points, or something like this, and that's. But yeah, but here, I mean, the fact that there is a rational point that sort of ties your hands behind your back. There are a lot of methods for proving that varieties do not have rational points, but we're obviously not going to be able to use any of those for these curves. All right. So right, and yeah. So in fact, maybe I can say there's also Bhargava has proved a theorem that looks similar to this, except for even degree hyperelliptic curves. And in that case, the theorem is that most even degree hyperelliptic curves have no rational points. But the methods used in that theorem and this theorem are completely different because, well, they have no rational points. So in fact, what he does is he uses the Chevalier-Vey method and passing to degree 2 covers, and then he shows that each of those degree 2 covers has no local points. And so that's well, I mean, you have to do a lot of work in order to make that work, to say why that works, but that's ultimately what he shows. Okay, so all right, so and maybe I can say also before we proved this, Bhargava and Grouse also they proved a weaker form of this, showing that a positive fraction of curves had, well, maybe not just one rational point, but they could show that a positive fraction had at most 3 rational points. But as I'll explain, you have to do some more work you have to do a substantial other amount of work to get to this. All right. So as I said, the method of proof is going to be Chaboty's method. So let me explain what this is about. So if you have the curve, you can and we have one rational point, you can embed it into its Jacobian by using this one rational point. And so each p in terms of classes of divisors, it goes to the class of this degree 0 divisor. And let me let R be the rank of the group of rational points of the Jacobian. And also for before specializing to the prime 2, let me just talk about the Chaboty's method in general, just to review what this method is. So you fix a prime p, and then you look at everything p-adically. So so the picture is this. You have, so this is supposed to be this p-adic Lie group. I guess maybe this is a two-dimensional Jacobian. And then you have inside this, you have the curve. You have the p-adic points on the curve. So let's say this is C of QP. On the other hand, you have the Mordell-Weil group, which is, let's suppose, just for the sake of this picture, let me imagine that the group of rational points is of rank 1. So you have a point and you have all its multiples. But one of the nice things about working p-adically is that these multiples do not fit over the real numbers. If you did this, the multiples would probably they had a good chance of filling up the entire. They'd be dense in the whole thing with a good. But p-adically they all line up into a one-dimensional analytic subvariety here, and so the closure of them, the closure of the set of rational points will be. Will look something like this. So in general, what happens is that this group, it has a finite index. Well, it's a compact group. It has a finite index open subgroup just by looking at that's isomorphic to just a direct product of copies of ZP. So that just follows from a formal group, and so okay. And as a consequence, this thing is of dimension G as a manifold, as if you think of it sort of as a naive QP manifold. So, and on the other hand, if you take the closure of the rational points, because you can, I mean, to understand this, you can look what happens inside this open subgroup, and there, if you're just taking the integer combinations of points, and then the closure will just be the ZP linear combinations. So this will be it'll be like a ZP, at least in this part of it, it'll look just like a ZP submodule of this, of rank, well, at most R. I mean, it could be less than R because there could be Z independent things that are ZP independent, and that actually happens sometimes. So anyway, so it looks like this, and then of course the curve itself, that's a manifold of dimension 1. And so, well, just based on dimensions, you would expect then, well, maybe that the intersection should be finite if R is less than G. So, yeah, and I guess I can put these all together into a diagram. Let's see. I think I want to. Let me use this board again. So this diagram is going to grow as the talk goes on, so I want to use a big board for it. All right. Okay, so I want to understand the rational points, and I know that on the one hand it injects into the rational points on J, and which you can include into the closure in the p-adic points, and so here are the p-adic points, and on the other hand this also injects into the p-adic points in the curve, and okay, so obviously the rational points of C must lie in the intersection of these two groups mapping into here. That's what's shown in the picture. All right, so okay, so I guess what I wanted to say here is that so at this point I can say, so Chaboty proved, I mean, heuristically this makes sense, but you can prove this, that if the rank is less than genus, then so that you expect at most a zero-dimensional intersection of these two subsets, then in fact this intersection is finite. And therefore, so that means that C of Q is also finite. Okay, so this is a way to prove faulting theorem, at least in a special case, when you have this kind of condition. Okay, so now in order to prove our theorem, though, we want to prove that this has only one rational point. So that means we'll need this intersection to be just consist of that one point. And well, all right. So to do this, we'll need to know, but we'll have to know not only how this looks p-adically, but we'll have to use some global input too to know how sort of in which direction this subgroup is pointing. I mean, it's not enough just to know that this has low rank, because even if it has low rank, if it happens to be, if that blue closure of the rational points is heading straight into, if it's pointing straight at some other p-adic point on the curve, then you will not be able to prove that the only intersection point is at origin. So all right. So how do we understand this? So all right. So let's. Well, I mean, the group law and the Jacobian, you can to understand that, you can use the formal logarithm map. So there's a homomorphism, or simultaneously which is simultaneously a local diffeomorphism that goes from QP, J of QP to just a vector space, which is really just the tangent space of the Jacobian. That's the logarithm. So I mean here, you can describe this map sort of explicitly in terms of p-adic integrals, where you choose a basis of 1 forms on J, and then you well, I mean, you have to make sense of what this means, but so anyway. So then anyway, there's some notion of integrals. So here, this omega 1 through omega g, this is a basis of the space of 1 forms. And okay, and you can say that the kernel of this logarithm map. Well, actually, before I say about the kernel, let's ask what the image of this map is. I mean, this is a compact group, so the image is going to be some, and it's a local diffeomorphism, so the image is both compact and open, and therefore the image is just going to look like it's going to be isomorphic to zp to the g. And by changing the basis here, I can choose this basis so that the image is exactly, so the image of this log map is exactly zp to the g. So okay, so let me now draw this in the picture as well. So now I have a surjection given by this p-adic logarithm map going to zp to the g, and the whole point is that this straightens out the group law. So whatever the group law is here, now it just becomes addition over here, and so that's why this is helpful. Yeah, and also not too much information is lost. I mean, this map does have a kernel, but the kernel is just the torsion subgroup of J of QP, which is a finite group. Okay, so right. So now, as I said, in order to control this intersection, I need to know something about the direction that the Mordell-Weil group is pointing in this space. And actually, well, you don't need to know it exactly which direction it's pointing. If you know that it's somehow, if you know it to some p-adic precision, then as long as it's pointing in a good direction, even if you know its exact direction, you can hope that maybe it's in a good enough direction that you can guarantee that it will not intersect the curve anywhere else except for the origin. So one way to think about it is that if you're standing at the origin and you look out into space, and you see this constellation, well, but you see this curve, the C of QP going along somewhere, and you just want to make sure that your Mordell-Weil group is pointing into some direction of space where the curve is not. And you can do you don't need infinite precision to say that it's not on that curve. You just need some. And so, in fact, it's hard to get information about the direction of the Mordell-Weil group, though, especially when you're varying the curve in a family. And so, in fact, what we're going to do is we're going to get by with knowing just one p-adic digit of information about the direction of this Mordell-Weil group. And so we're going to work with everything mod p. So okay, so let me take all of these groups mod p, and so okay, so this now surjects onto this closure mod p times the closure. And this maps to J of QP mod p times the. And I'll do that here too. So this also now surjects onto fp to the g. And so I have maps going down. And so instead of computing this sort of project, I'll call this p, which goes to pg minus 1. So it's just the map there. And I also have a map here, which I mean, And I can define this map actually so that it's defined everywhere except for the origin. Because if you have something that's not the origin, you can scale it by a power of p to make it so that it reduces to some point here. OK, so that's what this map rho is. And I'll call this thing, yeah, so let's call this one, this map here. There's another partially defined map. It's this one I'll call rho log. Because that's what it is. Okay, and so this one's going to be defined except on the torsion points, because the torsion points are the ones that go to 0 here, where this map is undefined. So these dotted maps are not defined everywhere, and so now the idea is to show that these things do not intersect the images of these two things intersect only in that one point. I will want to show, what I'll actually show is that when you push everything, both of these sets into here, then they do not intersect. I mean, the 0 has sort of gone away because it's not defined there. So.
Can't you have some p-torsion where this g cube is bigger?
Right. You have to worry about the torsion. There's going to have to be a separate argument to deal with the torsion subgroup, because once you go over here, you don't see the torsion anymore. And so I'll have to also argue that there are no torsion points on the curve. And so we'll need a separate argument for that. That's right. Yeah. All right. So. And OK, so now how are we going to control? So as I said, we need to control the image. Well, we need to actually, what we're going to do is control the image of the Mordell-Weil group in here. And in order to do that, well, we need some sort of bound on the Mordell-Weil group. And really, the only way to get bounds on Mordell-Weil groups is to use Selmer groups. So that's going to be what we'll use. So the Selmer group fits into this picture here. So let's put the Selmer group. The p-Selmer group, well, it accepts there's an injection like this, and then this goes, well, and there's also a map like this, which I'll describe. Well, maybe I'll describe this in a little later, but yeah, OK. So for now, so what is this Selmer group? OK. So just a quick review of Selmer groups. So if you have the multiplication by p map on the Jacobian, so you can take cohomology of this, and you'll get an injection of this into H1Q, the cohomology of the p torsion, and I mean, you would, in order to bound the Mordell-Weil group, you'd like to understand how this sits in here. I mean, usually this, this is essentially always is an infinite group, so you need conditions to control where the image of this is, and the Selmer group is what you get by imposing the local conditions. So you can write the same sequence works over any extension of Q, and so you can apply it to all the completions and get the corresponding homomorphism here, and then this makes a commutative square. So where I'll give these things names. So maybe this will be called the co-boundary maps delta and delta prime, and this is restriction. And then the Selmer group is a group that's up here. Selmer group is contained in here. The Selmer group is contained in this H1, and it's defined to be the elements here that map into the local image here. So it's just the restriction inverse of the image of delta prime. OK, and then just by definition, there's an obvious map from this Selmer group. There's a homomorphism from here into J of QV divide by p times J of QP, just because, well, I mean, in fact, it's landing in the subgroup that's actually the direct product of these. So you can then just project onto one factor. OK, so right. So in particular, you could do it with v equal p. I mean, pretty soon we're going to take v equal p anyway, and to put that homomorphism into this picture. OK, so then. Yeah, and then you can compose it with these other morphisms. So this map here, I'll call this one sigma, and then this one. OK, so now I have a partially defined map going to here called p sigma, right. So, okay. So yeah. So in order to get p-adic information about the Mordell-Weil group, I need to take, as I said, I need to use this map. So I need to take v. I need to take v equal to p, and the other thing I'll want to use is some information about. Now I need to know some information about the Selmer group, and at this point I use. So we need to use a theorem of Bhargava and Grouse that not only estimates the size, the average size of a Selmer group, but also tells you a little bit about the position of the Selmer group. So let me state this theorem. So all right. So consider a family of hyperelliptic curves. So let's call it family F of curves of this type, these odd degree hyperelliptic curves. And the family is exactly the family that's defined by finally many congruence conditions. So in other words, by congruence conditions, I just mean coefficients, conditions on the coefficients. So I could just say that the coefficient of x cubed is congruent to 5 mod 7 and have finally many such conditions. And then I look at all the curves that satisfy those conditions. So OK, so then they first prove that the average size of the Selmer group in this family, even no matter what congruence conditions you impose, the average size of the Selmer group, of the two Selmer group, is 3. And they also say something about the behavior of this map from here to here. In the case p equals 2. So it's a little bit difficult to state precisely. So I think I'll say something that's almost precise. So okay, so how?
The counting here is you counting the coefficients of the polynomial.
Yeah. So I guess to make precise, I'd have to list the. It's an infinite set. So really, what I mean is I look at all the curves where the coefficients lie in are integers in some big box, and then I look at the fraction. I look at the average size for the curves in that box, and then I let the box size tend to infinity.
Naive height.
Yeah, it's some sort of naive height, right, in terms of the coefficients. No, actually, the way they do it is the leading coefficient is 1. So you have the go geometrically grow up like that. So anyway, that's the way they did it. But right, and so that's implicit. That ordering of the curves is implicit in a statement like this. Yeah. Okay. So what? So I want to say that what I want to claim is that the Selmer elements, the non-zero Selmer elements here, that when they map into here, they become equidistributed in some sense. But in order to say that, as you vary the curve, this is changing too. but if you vary C in a small p-adic family, then this remains constant. This is just a finite group, a discrete group, and it doesn't. This forms like a locally constant bundle of finite groups over the space of. Above the space of all hyperelliptic curves. So yeah, so that's what I want to. So that I need in order to formulate. So this is locally constant. Not just locally constant, but sort of in a canonical way, it's locally constant, as C varies viatically. Oh yeah, sorry. No, well, actually, this theorem actually applies to any v. So that I'm about to say, but this has to be 2. But this what I'm about to say here, hopefully, their theorem actually applies to any v. Eventually, I'm going to take v equal 2 because, yeah, I want v to be p, and I want this to be p as well. So that's going to force everything is going to have to be 2. This argument sort of barely works. There's no choice to make this argument work. Everything has to be 2, because okay. All right, so I want to say first of all this is a locally constant bundle of groups over the family over the family, and if you shrink it enough, then it's actually constant. And if we shrink, So I look at, I just look at a small enough. I just impose small v-adic congruence conditions on to make this family small enough that this is actually constant. And after doing that, I can say if we shrink f to trivialize this bundle, to make it really constant, to make these groups really constant in that subfamily. Yeah. So to trivialize okay, so they do this so that now that all these groups are just isomorphic to a particular constant group, and there's somehow a fixed isomorphism that works locally. So this holds for all the curves in this family. So then you can talk about the equidistribution of the Selmer elements when you map them all the way into G. So to be a little more precise, you will take the images of S under the composition where you map the P Selmer group. Well, I guess it's 2 Selmer group. So the 2 Selmer group of J into J of QV, mod 2 J of QV, and then follow it into G, just so that they're all lying in, all the Selmer elements are mapping into the same group. And so you take all the images like this, where so C is ranging over F, over this family, this small family, and we look at the height of the coefficients in a box bounded by X in some way, and then the S ranges over all the elements of the 2 Selmer group of the Jacobian of the curve, except for 0. I mean, we know where 0 goes. So, but the claim is that if you look at all the other Selmer elements coming from all the curves in this family, and you map them all the Selmer elements into G, then this, well, maybe this is like a multiset or something. Then this collection of elements, so maybe I should write. Well, anyway, I think you know what I mean. This multiset of elements, now it's a multiset in G, then this becomes equidistributed in G. In G, as you increase the size of your box, to include more and more curves in this family. Okay, so this is sort of the key global input that we need for this theorem. And as I said, we're going to now, because we're going to set v equals p equals 2. I mean, we need to get p-adic information about the Mordell-Weil group, we have to use v equals p, and in order to apply this theorem, we need p equals 2, so that this is 2. So everything is going to have to be 2, as I said. All right. So now I think okay. So now what can we say? So remember what we're trying to do. We're trying to control the intersection of these two things. To say that most of the time these yellow and blue curves in here, they intersect only in the one rational point of the origin. And we're going to do this by mapping everything into here and showing there's nothing left. The equidistribution actually follows out of just the computations that they do to prove the first part of the theorem. In fact, they get the first part of the theorem by essentially adding up all the. If you prove the first half of the theorem, you sort of prove the second half just as you're going along anyway. So you don't really have to do any extra work.
The mechanism counting something in a family.
It's the usual Bhargava Shankar kind of methods. So you find a.
There's some pre-homogeneous vector space underlying it.
Yeah, except it's not pre-homogeneous, but it's this co-regular, what they call co-regular. Yeah, it's counting orbits of some group on some affine space. So all right, so let's see. So okay, so so we want to say that the intersection here consists of just this one point, which would imply that when you map everything into here, you should have no points because the 0 point has disappeared. I mean, it's where this is undefined. So what I want to say then is that so what kind of conditions would you need to guarantee that intersection is empty? So, well, if this maps sigma that I've put into this diagram, the map from the summer group into here, into this fp to the g, if that is injective, and okay, so these are, and if also the images of the two-adic points in the curve under rho log, and so the image of the curve and the image of the are disjoint. If these are, yeah, so if you have these conditions, then you can argue essentially by tracing through the diagram, although it's a little bit, you have to do a little extra work because of the fact that but essentially it's by chasing through the diagram that you see that these conditions would imply that this intersection that we're interested in, this intersection that's supposed to contain the rational points, that this is, well, you can't quite say it consists just of the point infinity because of, as we said before, that this doesn't see the torsion points. Well, actually, it does see a little bit about the torsion points of 2-power order, but it completely forgets about the odd torsion point. So anyway, so all you can really prove is that this is contained in the odd torsion subgroup of this group. And so you need to combine this. Okay, so this just follows mostly essentially from the diagram, but then you also need another lemma that says to show that there aren't any torsion points in this intersection. And that's like a Mumford kind of statement, to say that there, when you have a curve embedded in, there should be no, and you intersect the curve with the torsion points, all the torsion points of the curve, then that should be, well, I mean, the theorem is, I mean, Mumford conjecture was that it's finite. But what I want to say here is that at least most of the time, the intersection is actually trivial. And so that's this lemma 2. So this lemma 2 says that for 100% of curves, this intersection is the same intersection, except now we look at it for so this intersection is actually, well, okay, let me say, I guess I should say this way. I can take all the two-adic points and take all the I mean, at this point I only care about the torsion points because that's all that's left, assuming that these are satisfied. And the claim is that the only points in the curve that lie on the curve are, well, there are the Weierstrass points. The Weierstrass points of the hyperelliptic curve will map to 2 torsion points, and so they could lie in here. So anyway, so they lie but those map to 2 torsion points, and so that's okay because this combined with this will imply, if both of these conclusions hold, then you'll know that this intersection consists just of the point, the origin, the point infinity on the curve. So, all right. So, sorry, where? Yeah, G is the genus, but this, I'm not saying that this is isomorphic to this. It's a quotient. This FP is just, everything in this row is just the previous row modulo p times what's above it. So this is, what do you say?
But you have to divide into 2 p of
Yeah, so okay, so this map is just log, this map is the same as this map tensored with FP. Sorry, so yeah, this map is not injective. In fact, there's a little surjective sign on it. So yeah, I'm aware that this is not necessarily injective, but it's okay. So in order for lemma 1, my hypothesis for lemma 1 is that the map from this Selmer group into here is injective, and so that's going to be good enough to imply these conclusions. So, okay, but now, I mean, in order to finish this, so now in order to finish the proof of the theorem, I need to understand I need to know that for most. Okay, maybe I should say a little bit. I mean, lemma 1 just mostly follows from the diagram. The proof of lemma 2 is some sort of, well, there are different ways to prove it. This is like a generic. This is asking like what happens in the Money-Mumford conjecture if you apply to the generic curve, the generic hyperelliptic curve, and can you prove that this intersection is trivial then, or it consists of Weierstrass points then? And there are a couple of arguments you can use there. You can do some. I know of two approaches. One is sort of a degeneration approach, where you degenerate your hyperelliptic curve to something. And another way to do this, another way to do it is to use a monodromy kind of argument, where you argue that if there are any torsion points on the Jacobian that also lie in the curve, then all of their Galois conjugates will lie on there. But if you know, for the generic curve, for the generic hyperelliptic curve, you have these big monodromy theorems that tell you that torsion points, they have lots of Galois conjugates, and they have so many that there's no way they can all lie on the curve, and so you can use some sort of so that's another way to prove this. Okay, anyway, but even after, but once we're not done yet, because we still need to, this holds for 100% of C, once you know that it holds for the generic one. But you still need to know that most of the time these conditions hold. And for this, we're going to have to use this Bhargava-Grouse theorem. Bhargava-Grouse tells you, for example, that a typical curve does not have very many two Selmer elements. On average, there are only 3. And that's good because they're mapping into this big space of a size about 2 to the g. And they're also mapping in there kind of randomly, according to the second half of the theorem. So the injectivity is not going to be a problem. That's just to say, you have only about 3 elements, and they're mapping in here in a random way. So most of the time, there are going to be no collisions. So that part is OK. But the hard part is the second condition. How do you make sure that these randomly mapping things in here, that they don't hit the image of the curve in here? So you can think about it in terms of space again. If you're sitting at the origin in J of QP and you're looking out in space, well, you have these, and you're watching what happens as you vary your curve. And these Selmer elements are sort of they're bouncing all over the sky, and well, there are only 3 of them. But on the other hand, you also have this curve, this p-adic curve and you need to know that this curve is not winding around. You have very bad vision since you only can see one p-adic digit and as you're looking out, and also p is 2, so it's especially bad. But you hope that. But it could be bad though if the curve is such that the curve is winding around so much in space that it covers the entire space. Then it doesn't matter how much how random your Selmer elements are going. You need to know that they're not going to. Yeah. So what remains to be shown is that.
Actually, sorry, you use the 3 or the proof? You don't actually assume.
It doesn't need to be 3 as long as it's something small. But what?
But you're not going to use it. You're going to use the method, or you're going to actually use the theorem?
No. I'm going to use the fact that it's a small number. I'm going to use the theorem. Reuse the theorem.
Maybe you will use it to note outstanding with genus 3 things.
Yeah, actually, yeah, that's right. Well, so that's right. To know it's for genus, for you, you're right. Yeah, so that's exactly right. Because this is not so big when g equals 3, and so you need. In fact, this is exactly why the proof breaks down for genus equals to 2, and then the things just get too small, and then the curve is. It's just. So all right. And you can also start to see why this argument becomes better and better. I said at the beginning that the probability tends to 1 as genus gets bigger, and that's just because this space that we're mapping into is getting bigger. So, okay. So, but as I said, the last thing we need to do is argue that. So you have these random Selmer elements in this big space, but then we need to know that the curve itself, the p-adic points of the curve, when you look at it sort of under this log map and then reduce mod p, we need to know that it's not covering the whole thing, or it's not covering. Actually, we want to show, if we want to get asymptotically 100%, we need to know asymptotically that the image of this is not like a positive fraction of the space. So, okay. All right. So in fact, to be precise, so I mean after, okay, so you use, so okay, maybe I'll write down what I was saying. So by the Bhargava Grouse theorem, that already tells you that this map sigma is usually injective. So with probability that becomes better and better as G grows, and it also tells you that the image of the Selmer group under this P sigma map is usually small, and it's also random. So so the final thing we need to say something about is about the image of the. So what remains to finish the proof, there's only one thing we need now. It's that the average size of the image of the curve under this row log map, we need this to be small compared to the size of the whole space, so that 3 random things are not going to hit it. So we need this to be little o of o to the 2g. And so what we actually prove is we show that this average is at most 6g plus 9. And so let me now explain where this comes from. Okay. Okay, so first, as a warm-up, let me think about the case. Suppose that C has good reduction at 2. So if you have at 2, well, I mean, what does C of Q2 look like? Well, it looks like a bunch of residue disks. Okay, so this is just a, and then there's a reduction map to the F2 points, which I'll, okay. Okay, so these are just the, I don't know, three residue disks, and so to prove that the image of this row log map is small on this space, I'll just look at the image of each residue disk and see how big it can be under this map when I take this thing and map it into here. So right. So we'll need then to show, well, that to control the entire image, we'll show that the number of disks here is small, and then also show that the row log on each disk has a small image, so that the row log of each disk is small. And in the good reduction case, number 1 is very easy, because the number of disks is the same as the number of F2 points. And these are F2 points on a hyperelliptic curve. And there are only 2 such, there's a 2-to-1 map from C to P1. So, and P1, we know how many points P1 has over F2. So there are 3 points here, so this is going to have at most 6 points. In fact, it actually is at most 5, because in infinity there's only 1. So, all right, so this is, so okay, so this part is okay. So in the good reduction case, we know that the number of F2 points is at most 5. And then we'll have to use some argument for this. Okay, and then you have to use some argument to understand what this map does on each residue disk. And okay, so for that, let's. All right. So okay, so what does this row log map look like on each disk? So if let's first look at the log map. I'm restricting it to one of the disks on the curve. And so what does the log map look like? Well, I mean, it's the way the log was defined was by integrating one forms on the Jacobian. And if you want to restrict that to a piece of the curve, then you can just pull back the one forms and integrate the one forms on the curve. And so this is the same as integrating certain power series, certain one forms. So, and because we're doing it inside one disk, you can just write these differentials formally. You can do these periodic integrals formally in that disk, just by integrating power series. So integrals of power series, where these things come from the basis of one forms on the curve. So all right, so you have this map looks like this with these WIT being in their two-adic power series. And OK, and if you but we only care about what this logarithm does after you map it here, which is well, dividing out by any excess power of 2, and then just and then just looking at it. So for that, you just need to. It's enough to, because we're working two-adically. It's enough to see what this is up to 1 units. Up to 1 units, because that won't change. If you change this tuple for any particular value of this, any tuple, if you change it by 1 units, p-adic 1 units, then the image in here won't change. So I only need to understand this up to 1 units. And up to 1 units, you can understand this. You can replace the values of these by values of polynomials. And then using the fact that these come from one forms, which have a limited number. I mean, they have the number of zeros of each thing is bounded by something, by 2g minus 2. Then you can argue that these are polynomials of bounded degree. So where these, say, you can replace. If all you care about is the image, under this in here, you can replace these power series by polynomials, and then so then you have a. So then the question is, what? So now you have a little sort of an elementary lemma that says, if you have a map, if phi is a map now, well, I'll just view it now as a map from P1 to P1 to PG minus 1 over QP. And it's given by this tuple of polynomials. So with bounded degree, I mean, I said they're bounded really by 2g minus 2. You need to bound. We need to know how much of the sky they sort of fill up. How much can a curve, a copy of P1 under this polynomial, how much can it fill up the sky? And the answer is that it's at most. So if you take the p-adic points on this, and you then this thing is at most np plus 1. And this in fact this is bounded sharp. So I mean, this would be obvious if this map itself sort of had good reduction. If it because then you could just look at. I mean, we want to know where the FP points in the image of this thing are, sort of. And so it would be essentially, if this had good reduction, you could just say, OK, we have p plus 1 points here, and then they map to p plus 1 points here, and that would be the entire image. Then the only, I mean, it's true. But if this morphism has bad reduction, then what you have to, then the way we do this is by viewing this as a rational map from P1 over ZP to here over ZP, and then you view this as an arithmetic surface, and you blow up. I mean, to resolve the indeterminacy of this rational map, and you count how many FP points you have on the special fiber of that blow up, and you can control the combinatorics of that in terms of the degrees of this polynomial, and then this comes out of this. So OK, I'm not going to do the details of that because I'm almost out of time, but I'd be happy to say more if you want later. OK, but we're still not done because this handles this. Well, OK, so this lemma, it tells you what the image. It controls the image of this log map on one residue disk, and then we said, OK, in the good reduction case, we have only 5 residue disks to consider. But now, if you really want to get something, if you want to get a theorem that works, that asymptotically gives 100% as the genus goes to infinity, it's not good enough to consider the good reduction curves, because there's a big positive fraction of curves over Q2 that has bad reduction. And in fact, it's not even enough to look at nodal curves with nodal reduction, because that's still only a positive. It's still not 100%. In fact, so 100% asymptotically, you have to look at curves with bad reduction at 2, with arbitrarily bad reduction at 2. And you have to control the size of these. And so, yeah, so what happens is I mean, the idea is similar for bad reduction. There's a similar picture. I mean, again, this handles what happens on one residue disk, but the problem is that you have the number of residue disks can be growing. So with bad reduction. And so what you need, except that as I said, the problem is that except the number of disks now. Well, you have one disk for each smooth point on the, well, if you choose a minimal proper regular model of the curve and look at the smooth locus and count the F2 points, then those are the residue disks that contain 2-adic points. And we need to know, we need to control this. So this C is this minimal proper regular model. Okay, so, well, there's, so the last thing I need to say is how, you can't bound this uniformly because, this could be arbitrarily large, but luckily we only need to do it on average. So it's good enough if the average of this is small. And so, finally what we do then is we prove a theorem. This is actually maybe one of the technically most difficult technically involved part of the proofs, because we have to look at a completely random curve over Q2 and calculate or estimate the combinatorial complexity of its minimal proper regular model, and to count the number of smooth F2 points on it. And anyway, so we eventually prove that this average is, surprisingly, it actually turns out, we prove it actually it's less than 3, which might be kind of surprising since it's even less than the average for the good reduction curves. So there's a reason for this, why you get, you'd expect that maybe there would be more because you have some bad reduction curves that have more for which this is huge, but somehow the average turns out to be even less than 3. Okay, so now this really does finish the curve. Finish the proof, because this tells you this bounds on average the number of residue disks, and then this tells you that the image of the row log map on each disk is small, so that altogether this row log map is covering only a small part of the sky, and then you have these about 3 random Selmer elements that are going to miss it most of the time because the image of row log is so small, and so then that finishes the proof. Okay, I'll end here. Thank you.